Okay, we're doing 6.4, the exercises. Number 1 says there's a tank that's an inverted right circular cone. Height is 5 meters. Radius is 4 meters. It's filled to 3 meters deep. Of hot chocolate. The density, so this is a mass density, so 1070 kilograms per meter cubed. And we're going to work, so we have to do a force times distance to get work. Force in the metric system is newtons. Now, Newton is a kilogram meter per second squared. Now, kilograms times gravity in the metric system is meters per second squared. So, a kilogram meter per second squared would be a newton. So, this would be a force if we didn't have the meters cubed. Meters cubed is the volume. So, we need to talk about the volume. And that's going to be the volume of a slice. And we'll just take a slice right at the top. If I put my axis with y positive here, as the book does, and x positive down here, then this would be x. This would be a thickness of dx. The radius would be y. And so the volume of this disc that we're going to have to use a force to lift it up to the top, the volume of the disc is going to be pi y squared dx. So that's meters times meters times meters. Cancels that. Excuse me. Which gives us newtons only. So that's the force times the distance we have to lift this disc, which is up x. And that would be meters. So we have Newton meters. So the answer to this will be in Newton meters, which is the same as joules. So you can do Newton meters or joules for the units. That's just one disc. We want to do all the discs from here down to the bottom. And so we have to add them up, and x is going to go from down here, 3 from the bottom, the whole thing's 5, so that's down from 2 to 5. Now, all of this stuff is constant, so we've got 1070 times 9.8 times pi, integral from 2 to 5 of, we got a y. We have an x, but we got to take care of this y, dx. How do we do that? Well, there's a couple ways to do that. We can think of this as a point on the y-axis. X is 0, y is 4. Or we can think of this and this as a point on the x-axis, which is 5 and 0 in the y. And we can use those 2 points, 0, 4, and 5, 0. We can look at the change in y, that's going -4. The change in the x is +5. So the slope between these two is -4/5. Y equals -4/5 x plus the y-intercept, which was 4. Now I know this doesn't look like a negative slope, but remember, x goes this way, y is this way, and that's a negative slope going through 4 and 5. So sometimes you have to kind of turn your head to see how that's working. Or turn your paper as I did. Now, we could have also done it with similar triangles. This is y. This whole length is 5, and that's x, so this piece would be 5 minus x. So we could set up the ratio y to 5 minus x equals 4 to 5 on this triangle that's similar to this one. And if I multiply both sides by 5 minus x, I get y equals 4/5 times 5, which is 4, and 4/5 times a minus x, which is minus 4/5 x. So for the y squared, I need to put in one of these two, minus 4/5 x plus 4 squared. I can type that into my calculator, or I can square this and distribute the x and integrate, or just type this in the calculator and I should get the answer. And remember, the units are joules or Newton meters. That's number one. Number two. On this one, we have a oil tank that's an upright cylinder. So it's going to look like this. It's buried, so it's 10 feet beneath ground level. And the tank has a radius of 4 feet and a height of 12 feet. And the current level in the tank is 10 feet deep. And the density, now this is a weight density, is 50. Now pounds is a force, so we don't have to multiply by gravity. That's already a force. Weight is a force. All we have to do is get this off of here, and then we'd have the force for the work, force times distance. Pounds would be a force. So we need to multiply by a volume. And the volume we need to find is the volume of the slice we're going to take up to the top of the ground. Now, if I put my coordinate system, I don't know where you want to put it. We can put it here. So this would be the y, this is the x plus ins. So the thickness of this disk would be dx. If you put y here and x here, then it'd be dy, but it doesn't matter a whole lot. So this is a disk that's a cylinder, so that's pi r, which is in the y direction, but it's always 4, so 4 squared, pi r squared, times the thickness. So that's meters twice, and that's meters, so that counts, feet squared times feet, feet cubed. So the cubic feet are going to cancel, and now I have just pounds, which is a force, times the distance I need to lift that, which is going to be, if I put my axis like this is x, and I need to lift this disk x plus 10. Okay? And if I set it up this way, I'm going to add all these disks lifted up to here for x starting at not 0, because we're down 2 feet, from 2 to a depth of 12 feet. Now you can move this dx out here. You can take all these constants out, and so you'd have the integral of x plus 10 dx evaluated from 2 to 12. Pretty simple to do. 3. Now they want us to empty a rectangular pool. Okay, so the rectangular pool will be something like this. It's 50 feet long, 30 feet wide, 8 feet deep. It's filled with water up to 6 feet. And water density, now this is a weight density, so we don't have to put the gravity in, it's already in that, 62.4. Pumped all the water over the top, so we got to lift it to the top. So if I don't really need the y, I just need the x, and if I call that x, and this is x at 0, and this is at 8, then 62.4 pounds per cubic foot. So if I can find the volume of my slice, I'll just take a slice right off the top. Its volume would be 30 by 50 by dx. I should use a dot so it doesn't get x times dx. So there's a volume times the pounds per cubic foot, makes it just pounds, which is a force, times the distance I'm going to lift that disc, which is going to be x, and it's going to increase. It's going to be 2, but it's going to increase as we take water out, and we're going to add up how all these little small slices of the water from, if x is from here, we're going to go from 2 to 8 to remove those 6 feet of water. All of this comes out, and this would be just the integral 62.4 times 30 times 50 times the integral from 2 to 8 of x dx. That's 1/2 x squared. Put in the 8, put in the 2, subtract them, times this, and we'll get the work, which will be in, the unit on that will be pounds times feet, so they're called foot-pounds. Okay, now we can go to number 2. Or number 4, excuse me. We just did 1, 2, and 3. Number 4. Clean sheet. Okay, we have a cylindrical tank. And we're going to do different heights. So, cylindrical tank. It has a height of 11 feet. A radius of 4 feet. And water density is the 62.4. The work required, the tank is full, pump it to the top. So we take a slice. If I put my coordinates here, with this being x positive and this being y positive, then the slice, we'd have the density 62.4 pounds per cubic foot, so we have to take it times the volume. We're going to have a slice here that's dx thick and has a radius of 4, so it's going to be pi times 4 squared, pi r squared, times the thickness. That's the volume of a slice. That's the weight density. So weight density times volume is a force times the distance we have to lift it, which will be, since it's full, we're going to have to start when x is 0 is the distance we're going to lift it. But it's going to be always x on this, and x is going to go from 0 to 11. And all these are constants, so it's just going to be the integral of x dx, which is 1/2 x squared, evaluated from 0 to 11, times that number. B. Now it's full, but we have to pump it to 6 feet above. Well, that just adds to the distance, so it would be the integral from 0 to 11, pulling all those constants out, but I'll write them in. 62.4 times pi times 16, 4 squared, times, I'll put the x in here, the x plus 6 more feet to get it 6 feet above the water, so it'd be x plus 6 dx. Okay, C. The depth of the water in the tank is 6 feet, so now the water's only 6 feet deep, and pumped over the top of the tank. Well, this is to the top of the tank, but instead of going, so we're going to have to pump it 8, but pump it to the top, which is x, but we're starting at where it's 6 foot from the bottom, which means it's 5 feet from the top. So we just change this to 5, and there's the formula for the work for pumping the bottom 6 feet out of the tank. 5 to 11, 6 feet of it. Okay? That's number 4. Number 5. Number 5, we have a lobster tank in a restaurant. It must be a rectangular. Don't know why it say it must be, but I believe it is because they talk about it being 1.25 meters long times 0.5 meters wide times 90 centimeters deep, which is 0.9 meters. And water density, they put water in it. And this is mass density. And they want to know, find the water forces on the bottom of the tank. So the total force will be the total weight of this. And this would be mass. To get weight, we have to take it times 9.8 meters per second squared. So that makes this Newton a weight force. So it's 9800 newtons per meter cubed. Now what we have to do is take it times the volume of the tank, and we'll find the weight on the bottom. And the volume of the tank is going to be 1.25 times 0.5 times 0.9. That's meters, meters, meters. So that's meters cubed times meters divided by meters cubed. Cancel, and so we just have to multiply that out. No calculus involved. On each of the larger sides of the tank, the force is. On the larger sides of the tank, this side, this is a smaller side, this is large. So we want the larger side. To get the pressure on that, the force on that, we'd have to do the weight density, 1000, actually 9.8 times 1,000. That would be newtons per meter cubed times, so we're going to add up little rectangles on here. So the pressure on that rectangle of the side is going to be this times the depth. So if I put x at the surface, this is x. So times x in meters, the meters, one of the meters cancel, and I have the pressure, 9.8 newtons per meter squared. So then I just have to take it times the area to find out the pressure on that skinny rectangle. And its change is dx. That's the height of the rectangle. The length of the rectangle is 1.25 times dx. So we have the how deep we are times the length times the height of that rectangle, and that cancels that, and that would give you a Newton, which is a force. We just have to add up all of those on the side here where x goes from 0 to 0.9. So that would be the force on the one of the larger sides, and would be the same on the other large side. And then they say how much on the smaller side. The only thing that would be different, still x deep, still dx thick, but it would be only 0.5. So I'd change this to 0.5 to do the force on the smaller side. And the force would be in newtons, because meters, meters, meters cancel the meters cubed and leave just newtons. That's number 5. Number 6. And I had an interesting conversation earlier today on number 6. Come on. When the student came in and said, I can't get the answer in the back of the book on one of these. And I couldn't either. So I don't think the book is correct on one part of it. Okay. So they're saying, for this one, we got this equation. And if you graph it on the xy axis, xy, it'll do something like this and then it'll get crazy. This is 3, and this is, if you do calculate the intersection, you get 1.845, I believe, approximately. You have to find that intersection. Then they say turn that sideways and rotate that around the x-axis, which would cause it to look like that. And it would be a circular tank. And that's what they want you to picture in this. Rotate it 90 degrees, so the positive x-axis is straight down, we've got that. And the y-axis points to the right, we've got that. And we make a solid, and suppose, and this is a storage tank, and suppose that the resulting tank is filled to a depth of 1.5 feet. So this is 1.845 feet deep, the total depth. And it says is filled to a depth of 1.5. Okay, this is kind of small. I'm going to get a little closer here. Help you see my picture. Okay. And we have the weight density 62.4, and what's the work required to lower the water in the tank until it is 0.5 feet deep by pumping water out of the top of the tank? So we got to do force. Fortunately, we have 62.5 is a force per foot cubic feet. So if we take it times if we take a slice off of this, it's going to be volume of the slice is going to be pi r squared times the thickness of it, which will be in the x direction, so dx, and we're going to lift it from the slice to the top, which the top has x right there, so it's going to be from lifted a distance of x. So these volume units will cancel the feet cubed, and this will be in feet, so we'll get foot pounds, which is work in the English system, a foot-pound. Now, what are our limits on our integral? Well, it's going to be, we're going to start down here, 1.5 from the bottom, and if the bottom is at 1.845, we're starting at 0.345. 1.85 minus the 1.5 is 0.345. And we're going to take that one out, and then we're going to keep pumping until we get to down, it said lower to a half a meter deep. So if I take a half off of this, that would be 1.345. So everything's cool here except the radius, which I called r, is in the y direction, so it's y squared. But y, according to the original problem, is 3 cosine x to the third over 5. So my final integral for this one would be the integral from 0.345 to 1.345. The 62.5 would come out. It's a constant. The pi would come out. It's a constant. R squared would be the 3 cosine x to the third over 4. That's y, or r, squared times x dx, and then it's a calculator problem. Type this into y1, and you can put in this times this into y1 and calculate the area from 0.345 to 1.345, and you get an answer that's not matching what's in the back of the book or in the answer section. But that would be part A. Part B. So now we have the same tank, same rotation, but now, well, not the same tank. We have the shape is the same, but they're putting it on a end of a, that's the end, and the tank is 10 feet long. Okay, so it looks something like that. And this is 10 feet. And this is that same equation for the shape. Y equals 3 cosine of x to the third over 4. So we're going to have a slice in here of water. I think we're doing this. Let's see. Suppose the resulting tank is filled completely with water. Find the formula that tells the amount of work required to lower the water by h feet. So I'm going to put y here again, x this way again. This is going to be x, and so we have to find the weight of a slice. So 62.4 is weight per cubic foot, so we have to take it times the volume, which is going to be, well, this is y, so it's going to be 3 times cosine of x to the third over 4. That's from here to here, but we want the whole width, so times 2. So that's this way. This way is 10. And the thickness is a dx, so height times length times width is a volume times the 62.4, which is the weight per volume. So this turns out to be just weight, a force, times the distance we have to lift it, which is going to be x. So this is all going to be times x. We usually put it inside, but I don't have room. And we're going to integrate this, we're going to take it, it's completely full, so we're going to go from 0 to however far down they want us to take it, h. And so this is what we'd work out. So we'd have to antiderivatives, plug in h for x, and then plug in 0 for x. And they just say, find a formula for it. So this would be the formula for the work to lower to h feet. Okay. C. Suppose the tank in part B is completely filled with water. Find the total force due to hydrostatic pressure on this end. Okay, so to do that, we're going to take just a slice. We're going to see what the pressure is on there. So we take 62.4. That's a weight density. We take it times its depth, which is x, and that turns out to be a weight per area, so that's a pressure on this rectangle, pushes on that. And if we take it times the volume of this slice, or the area of this slice, we get the force, just the pounds, and all the other units are canceled. So the area of the slice, it's still dx thick, and its width is still 2 times the cosine of x to the third over 4. So 2 times this is how long it is. The height is dx. That's the area, and the distance down is x. So that tells you how much pressure when you take it times this, and this takes the area off. And so this leaves just pounds as the units. And we're going to integrate this for x going from 0, was it full? Completely full. How much pressure on one end? So 0 to the full 1.845. Now, to get the 8.45, you need to actually graph this. In case you didn't catch that earlier, y equals 3 cosine x to the third over 4. Plug that into the calculator and see where it crosses the x-axis. It looks like something like this, and you have to find that x-intercept to get that low spot on it. Okay, so that's 6, 1 left. 7, cylindrical tank buried on its side. So now we have a tank that's laying this way. Okay, it has a radius of 3 feet, has a length of 10 feet. It is completely, I'm going through the reading here, it is completely filled with water, and the water has the density, of course, of 62.4. And the top of the tank is 2 feet below ground, so the ground level is 2 feet higher. Set up, but do not evaluate, the integral expression that represents the amount of work required to empty the top part of the tank. So we're going to work in the top part, so we're going to do a slice here. So now I need to set my axis on this, and this time I'll still do the y sideways, but I'm going to put it at the center of the tank, just to make it a little easier. I'll put x positive down here, y positive here. Doesn't matter, I could put x positive up here. But here's my slice, and so this is going to be y. this will be x, because that's x, y, or x, yeah, because this is the x-axis, so I'm moving x and then y to get this. And 3 was the radius of the tank, which goes this way also. So 3 is here, 3 is here, 3 is there. So the relationship, let's first of all take the slice that we have to lift up to there. So the weight of the slice would go the length of the tank. So it's going to be 62.4 pounds per cubic foot times the volume, which is going to be 2y times 10 times dx, the thickness, that we're going to lift. So that's the force. Weight density times the volume gives you the weight, a force, times the distance we have to lift it. Well, this is now x. So this right here is going to be 3 minus x. And we have to lift it 2 more than that. So it's going to be, we're going to lift it 5 minus 5, which is from 2 clear to here, minus x. So we're going to lift it 5 minus x. And we're going to integrate all of this from, we're just emptying the top part of the tank, so x is going to go from 0, we've got to move this layer, all the way up to here, which is up to 3. Got to remove each of those layers. We have a y in it. Got to get that out of there. Well, we have a triangle here. X is here, y is here, 3 is here. So y is 3 squared minus x squared square root. 3 squared minus x squared square root, using Pythagorean theorem on this triangle. So that's what would go here, and then we'd have everything in terms of x. The 62.4, the 2, the 10 can be pulled out, the 5 can't. And so all of that would come out. On the outside, we'd have this times a negative x, and we'd integrate from 0 to 3, and we'd get our answer for that one. Whoop, 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 whoop. Setup. Do not evaluate. Integral for doing it, raise it. Oh, we have to lift it up. Not only the 2 to the surface, but we have to lift it up 4.5 feet more. So it's going to be 4.5 plus 2 plus 3, 9.5, minus however high the x is. So it should be 9.5 in there. I don't know why I saw that now and didn't see it earlier. Okay, and B. Now let's say the tank is only half full, they say. But the total force, hydrostatic pressure on the side. Okay, so now we're going to do a slice in the water. It's on this end, not the sides, against one end of the tank. So the thickness is dx, and we're going to be this deep in the water, which is x. So the hydrostatic pressure is 62.4 pounds per square cubic feet times x deep, which gives us the pressure, times the width, which is going to be 2 times 9 minus x squared. That's from here to here. Oh, the square root of that. That's from here to here, times dx, evaluated. So now we're going to have x go from 0 to 3. And that will get the pressure on the end. Okay.